In this session, we will continue our discussion with few of the fundamental aspects of matrix algebra. At least we will get the definitions clear, so that when they will appear in the later part of this course, especially when we will deal with iterative methods, we feel ourselves more conversant with these terms. So, we will discuss about the few more aspects, which are positive definiteness, singular value and condition number. So, let us consider a function which is a function of x and y, and it is a general quadratic function of x and y. F x y is equal to x square plus b x y plus c y square, does not have any other constant in this function. So, it is entirely varies with x and y, and we try to find out what is the minima of this function. Why the minima is important? Because positive if we say that this function is positive definitely, then we say that definitely this function is positive, that means it will always have a positive value. Now, if we look into this function f x y is equal to x square plus b x y plus c y square at x y is equal to 0 0, f of x y is equal to 0. So, the minimal value is not positive, we can get at least one location where f x y is 0. So, this function can be a positive definite function, that means it can only have positive values, definite does not have definite positive values. In a case where this f x y at x is equal to 0, y is equal to 0, x is equal to 0, y is equal to 0 is a minima. Then this is the minimal value of this function, that means every other value of this function is a positive value. So, the function except x is equal to 0, y is equal to 0 everywhere has a positive value. Positive definiteness will mean that the function will always have a positive value, or it should have a minima at x is equal to 0, y is equal to 0. So, this can be a function like this, a concave function where the minima is at x is equal to 0, at y is equal to 0. And how do I ensure that the minima is at x is equal to 0 and y is equal to 0? We will take the gradients, we will consider the gradients. So, you can see that at x is equal to 0, y is equal to 0, the gradients are already 0. So, del f del x is equal to 0, del f del y is equal to 0, because there is a quadratic function of x and y without any other constants here. So, these things say that there can be three cases, and we know that if first derivative is 0, it can be a minima, it can be a maxima, or it can be an inflection point. So, what are the tests that it should be a minima? The test is that the second derivatives should be greater than 0, and not for like with respect to x and y, and not for being an inflection point d2 f dx square into d2 f dy, del 2 f del x square into del 2 f del y square should be greater than equal to del 2 f del x del y. Now, if we impose these conditions on the function, this function, we will get that the first two will give me a is equal to 0, a is greater than 0 and c is greater than 0, and the third one will give us a c is greater than b square. So, if these conditions hold, then we will say that f x y is a positive definite function, that means it will definitely have positive value, we will know where it will have a negative value. So, we can say in R2 function f x y is x square plus b x y plus c y square, it is positive definite, that means it only has a positive value except x is equal to 0, y is equal to 0, that is the only location where it has a negative value. So, if we can represent this function as x transpose A x, where x y is the x vector. So, this is x transpose, this is A and this is x. Now, positive definite means it has a 0 value at the at x is equal to 0, y is equal to 0, which is the minimum of this function. So, if x is a non-zero vector, nowhere it has a 0 value, everywhere it is a positive function, it is definitely a positive function. And in that case, we write that positive definiteness means x transpose A x is greater than 0 for all x which is a non-zero vector. And in a higher dimensional space, this can be, instead of x in R2 and A being a 2 by 2 matrix, this can be a multidimensional matrix. X belongs to, or we can write this with the vector x belongs to Rn, and A is an n into n matrix. So, this x transpose Ax will give us Aij Xi Xj, and it will also be a positive definite matrix if x transpose Ax for any non-zero vector x, x transpose Ax is greater than 0. So, the idea is similar, that we have a matrix A which is pre-multiplied by transpose of a non-zero vector and post-multiplied by the non-zero vector, and the product which is a quadratic function of different x and y, or the quadratic function of different components of the vector x. This product is always greater than 0, that x is a non-zero vector. If x is a 0 vector, it is 0, but if x is a non-zero vector, this product is always greater than 0, or definitely this product is positive. Then the matrix A is also said to be a positive definite matrix. In that case, we write that A is positive Now, earlier we have seen that there are few conditions based on which, like when we took the function ax square bxy plus c x square plus bxy plus c square cy square, there are few conditions based on which we can say that x is equal to 0, y is equal to 0 is a minima, and therefore it is a positive definite function. X square plus bxy plus cy square will have a non-zero value for any other values of xy except the 0 0, and these conditions are a is greater than 0, c is greater than 0, and we got AC is greater than b square. So, that means the matrix A should possess certain properties based on which this will be decided, that x transpose Ax is greater than 0 for any x except x is equal to 0. And if we look into those properties, that there will be few tests on the matrix A, and we will see how certain parameters, for example eigenvalue or the determinant or the pivots of the matrix appear, so that we can say that x transpose Ax is a positive definite functional and A is a positive definite matrix. So, there are few tests. Each of the following tests is a necessary condition for a real symmetric matrix to be positive definite. So, each of these has to be satisfied. X transpose Ax is greater than 0 for all non-zero real vectors x. All the eigenvectors x, all the eigenvalues of A must satisfy. These are not necessary, all these are necessary and sufficient conditions. So, if at least one of these condition is satisfied, the rest are also satisfied, and A is a positive definite matrix. That means x transpose Ax is greater than 0 for all non-zero real vectors x. That is the first condition, which is same, which will be also satisfied if eigenvalues of A satisfy that all the eigenvalues are greater than 0. There is no zero eigenvalue, A is not a singular matrix, and also there is no negative eigenvalue of A. All the upper left submatrices of A, for example, if we have a large matrix A, all the upper left submatrix, this matrix, or maybe this matrix, all the upper left submatrix of A, if we take this diagonal, any matrix above this, will have a positive determinant. all the pivots without doing row exchange must satisfy dk is greater than 0. So, all the pivots should be positive pivots. Fifth is that it is for a real symmetric matrix A, it is positive definite if and only if there exists a matrix R which has independent columns, so that R transpose R is equal to A. So, R is also a square matrix. There can be a square matrix which has independent columns, so that A can be classified as, A can be decomposed as R transpose R, and that is for a symmetric matrix with real values. Then A is a positive definite matrix. So, if any of these properties hold, A must be a positive definite matrix. The last one is only for symmetric matrix. Symmetric positive definiteness has certain very interesting properties, and few applications of matrix solvers are specifically for symmetric positive definite matrices. We will discuss it later. There is another term called positive semi definite matrix, and positive semi definite means this is not negative. X transpose Ax is greater than equal to 0 for all x which is not equal to 0. So, it can be x transpose Ax is possible to have x transpose Ax 0 also, but it is not a what I will say, that it is not necessary that x transpose Ax is always positive, it can be 0 also, but it is never negative. And for real symmetric matrices, there are few tests for positive semi definite matrix. Again, we came to the paradigm of symmetric matrices, that x transpose Ax is greater than equal to 0 for all real vectors x. All the eigenvalues satisfy that the eigenvalues are non-negative, it is either greater than 0 or is equal to 0. So, A can be a singular matrix also. No principal submatrix has negative determinant. None of the pivots are negative. There can be 0 pivot, but none of them are negative. So, it can be a singular matrix, that is why there can be 0 pivot also. And there possibly exists a matrix R, which possibly have dependent columns, so that we can decompose A as R transpose R. So, few of these things have similarity with positive definite matrices. Only thing that positive semi definite matrix can be a singular matrix too, but positive definite matrix has no eigenvalue which is 0, all eigenvalues are greater than 0. So, it is definitely a non-singular matrix. So, we go to the next set of the next property which we are interested in, or this is not a property, this is decomposition of matrix. There is one particular operation on a matrix, and for if we can remember that for square matrices we obtained that A is equal to, we can decompose any matrix A is equal to vector x transpose lambda x, where x is a orthogonal matrix, x is the matrix combining the eigenvalues, lambda is the eigenvectors, and lambda is the eigenvalue matrix. In case of a rectangular matrix, a similar decomposition is possible, which is given as A is equal to u sigma v transpose. Instead of x transpose and x, we are using two different matrices u and v transpose, and instead of the lambda or the eigenvalue matrix, we are also using another different matrix sigma, where u is an m into m matrix whose columns are the eigenvectors. Now, they are not eigenvectors of A, because A is a rectangular matrix, we cannot have eigenvalue and eigenvector of A, but we can get eigenvector of A transpose. A is a u is a m into m matrix whose columns are the eigenvectors of u transpose. U is, and then U is also an orthogonal matrix. Why? Because A transpose is a symmetric matrix, therefore its eigenvectors must be orthogonal to each other. Similarly, V is an n into n matrix whose columns are the eigenvectors of A transpose A. V is also a symmetric matrix. So, the A transpose A is also a symmetric matrix. So, eigenvectors are orthogonal to each other, therefore, V is also an orthogonal matrix. And sigma is an m into n matrix whose first r diagonals are the square roots of non-zero eigenvectors of both A transpose and A transpose A. Depending on how many what is the rank of A, or how many independent columns or rows do A have, we can get non-zero eigenvalues of A transpose and A transpose A, and they will come in the matrix sigma. So, sigma will look like a square matrix, say we will have lambda 1 0 0 0 0 lambda 2 0 0, maybe 0 0 lambda 3 0 if sigma is a 3 into 4 matrix. So, depending on, and these 3 are the independent rows, number of independent rows and columns of A. So, depending on that, sigma will have non-zero eigenvalues, non-zero diagonal terms. For example, if I have something like a 4 into 2 sigma, A is 4 into 2, sigma will also be 4 into 2. So, this will be lambda 1 0 0 lambda 0 lambda 2 0 0 0 0. Only these two diagonals will have, these two rows will have non-zero diagonal terms. And these are diagonal elements which are the square roots of non-zero eigenvalues of A transpose and A transpose A. So, rather we should write that sigma will have the form of root over of lambda 1 0 0 0 0 root over of lambda 2 0 0, maybe 0 0 0 0 0, and lambda 1 and lambda 2 are eigen values of A transpose or A transpose A. So, A transpose and A transpose A essentially have same eigenvalues, same non-zero eigenvalues, because one of them will have a larger dimension, however, there will be 0 eigenvalues corresponding to that dimension nevertheless. So, we can get the first are diagonal elements which are square roots of the non-zero eigenvalues of A transpose and A transpose A, and these are called the singular values of A. The non-zero, to find out the non-zero eigenvalues of A transpose or A transpose A, given A is a rectangular matrix, and square root of the non-zero eigenvalues will be called as the singular values of A. And when we can decompose the matrix A as U sigma V transpose, where sigma is the matrix comprising the singular values of A, which are the square root of A transpose and A transpose A. This is called singular value decomposition. And interestingly, if we can take a square matrix A, we will see that this is very similar to a x sigma x transpose type of decomposition of A, where the matrix sigma will now compose the eigenvalues of A if A is a square matrix. So, it is defined for a general matrix which is a rectangular matrix, and we get singular values which are square root of the eigenvalues of A transpose and A transpose A. So, there are few remarks for a real positive definite matrix A. Positive definite means it is a non-singular matrix and it does not have a negative eigenvalue also. A is equal to U sigma V transpose is identical to A is equal to Q lambda Q transpose, where we can write lambda, we have seen this form earlier. Lambda is the eigenvalue matrix, it is a diagonal matrix whose diagonal elements are the eigenvalues only, and Q is an orthogonal matrix formed by eigenvectors. Q is an orthogonal matrix is formed by eigenvectors, that depends on if A is symmetric, then Q is formed by eigenvectors. If U and V give orthonormal basis of all fundamental subspaces of A. So, we have seen that sigma has r eigenvalues, r non-zero entries in sigma. Therefore, the A transpose and A transpose A will have eigenvalues, non-zero eigenvalues, which is exactly same as the dimension of the matrix, as the rank of the matrix A. Therefore, U and V will have same number of, because U and V are the eigenvector matrices, will have same number of independent eigenvectors. So, similarly that will be determined. First, r columns of U will give the column space of A, which is the number of independent columns, which will number of independent columns of A is basically R. So, first r columns of A will give will be the basis of column space of A, and m minus r columns will be, obviously U is a m into m matrix. So, m minus r columns will obviously give the orthogonal complementary space of A, which is the left null space of A. Similarly, first r columns of V will give the dimension of or basis for row space of A, and last n minus r columns, which will be the complementary part, which is null space of A. So, if we can do a singular value decomposition, not only we get the singular values which are eigenvalues of A transpose, but we can also get the fundamental basis for orthonormal basis for fundamental subspaces of A. So, their orthonormal basis, that means their independent spanning vectors, as well as each vector has an unit length and each vector is perpendicular to the rest of the basis vectors. So, you do not need to do a Gram-Schmidt type of operation to get an orthogonal set here, they are already orthogonal set. And matrix A, and this is a very interesting property, matrix A multiplies a column Vj of V to sigma j times of a column of U. Sigma j is, what is sigma j? Sigma j is the square root of eigenvalue of A transpose, or the singular value of A. So, A multiplied with V will give U multiplied by the singular value matrix, SVD matrix. So, AV is equal to U sigma. Okay. So, we will go to another third concept which I am supposed to discuss today, condition number, and we have discussed singular value mostly in two purposes. The main purpose is that when we look into condition number, which has a lot of importance in matrix solvers, that condition numbers can be estimated using singular values, but we will not do the detailed algebraic proof for that, but we will show the formula, we will show at the end how to express condition number using the singular values. This is the main purpose. However, there is another purpose, which is that any rectangular matrix can also be decomposed into three matrices, two matrices with orthogonal column vectors, and the third matrix, which is a kind of a diagonal matrix with few non-zero diagonals, and remaining terms are diagonal in this matrix. And by this decomposition we can get the basis for the fundamental subspaces of A, column space, row space, null space, left null space, basis for all these spaces can be obtained. And also AV is equal to U sigma, this relation says that I can transform one space to I can transform column space to row space or vice versa using this particular decomposition and the A matrix. So, this is in linear algebra, singular value decomposition pose a immense interest, and lot of theorems and applications of linear algebra depends on singular value decomposition. However, we tried to cover it very briefly, so that we are conversant with the definitions. That's the main purpose of this discussion here. So, we will go to the third topic, which is condition number. For a non-singular matrix, condition number is defined as the matrix norm of the matrix condition number of matrix A, matrix norm of the matrix A into it is dot product, or it is into the norm of the inverse of the matrix. It is not dot product, it is a simple multiplication matrix, because norm is a scalar quantity. So, multiplication between two scalars, one is the matrix norm of the matrix A, another is the matrix norm of the inverse of A. A matrix norm, we have looked into vector norms. A matrix norm is defined as a vector norm of, as defined using a vector norm, as matrix norm of A is the ratio of the vector norm of A x, x being any non-zero vector, divided by the norm of the vector norm of the vector x and maximum of that. So, we take any non-zero vector x and multiply with A, and the ratio of the norms, vector norms A x by x, and find out which one is the maximum of that, and we call that as the matrix norm of A. This in a sense can be thought, if we have a vector x, how much, to which extent, like if I have a vector x and when we multiply a vector with a matrix, this is again another vector. So, what is the norm of the product vector divided by the norm of the original vector, or how much the vector is being stretched when it is multiplied with that matrix. So, it is kind of a measurement of the stretching which is accomplished by multiplying any vector with the matrix, and what is the maximum amount of stretching when we do multiplication of the matrix. That is defined as the matrix norm. A matrix may have one first norm, second norm, p norm, infinity norm, same as the vector norm of the vector. So, what definition are we using on the vector norm, that will define that what definition we will be using for the matrix norm. If we use L1 norm for the vector, it is the first norm of the matrix. If we use L2 norm of the vector, it is the second norm for the matrix. If we use L infinity norm, that is the largest component of the vector, we will use the infinite norm for the matrix. So, it is it will go hand in hand. Condition number of a matrix measures the ratio of maximum relative stretching, which is norm of A, to minimum relative shrinking that the matrix does to any non-zero vector, such as A matrix norm of A into matrix norm of A inverse is maximum of A x by x, which is maximum stretching of the vector x by this matrix, into minimum of A x by x inverse 1 by minimum of A x by x, that is the minimum stretching possible relative shrinking using that particular matrix. A singular matrix will have infinite condition number. Why? Because A inverse, singular matrix means the inverse is A has a there is some 0 in A. So, multiplying a vector by a singular matrix will probably result in 0 stretching of that matrix, and A inverse will be 1 by 0, and therefore, the matrix will have infinite condition number. So, interestingly, we can say if A is singular, A x is equal to b is not solvable. So, if a matrix has infinite condition number, A x is equal to b is not solvable. A matrix which has very high condition number, it will be difficult to solve that matrix using any matrix solver. Low condition number or condition number close to 1 are designed by the matrix solvers. If the condition number is high, we call them to be ill conditioned matrix, and we can quickly show it later also. As a matter of fact, any matrix solver will probably not work well with that, with low high condition number matrices. If we use L2 norm for the vectors, or if we use 2 norm for matrices, we have discussed in detail about the norm of a vector. So, if you use L2 norm, that is, norm of a vector is square root of the square of all the components of vector. It can be shown that for an invertible matrix, the condition number is same as the ratio, sigma max by sigma mean, or the ratio of the maximum singular value by minimum singular value. So, that is one big importance of doing singular value decomposition. If we find maximum singular value and minimum singular value for any matrix A, its ratio is a good measure of condition number, and it is actually the second norm of the, if you use second norm for the matrices, it is the condition number which comes to the definition. A normal matrix is defined as a square matrix A is called a normal matrix if U A U inverse is a diagonal matrix for any unitary matrix U. So, trying to define a matrix, normal matrix, which needs definition of another type of matrix which is an unitary matrix, and U is a unitary matrix. U is a unitary matrix if it is a square matrix with U Hermitian is equal to U inverse. For real square matrix, U transpose is equal to U inverse, or U is an orthogonal Q matrix, then U is called an unitary matrix. So, unitary matrix is a complex equivalent of an orthogonal matrix. So, if A is if U inverse is a diagonal matrix, or for real matrix Q A Q inverse Q A Q transpose is a diagonal matrix, then A is called a normal matrix. If A is a normal matrix, if Q A Q transpose is a diagonal matrix, A must be a symmetric matrix, or if A is a normal matrix, A Hermitian is equal to A Hermitian A. For real matrix, A transpose is equal to A transpose A, then A is a normal matrix. And if it is so, then the condition number is same as the spectral condition number, or the ratio of the maximum eigenvalue and minimum eigenvalue of A. And we will very quickly check that what are the importance of having condition number, or having high spectral condition number or low spectral condition number of a matrix, or high condition number or low conditional number of a matrix. If a matrix has large condition number, the solution may be unstable due to small perturbation or round of error. For example, if I am solving some equation Ax is equal to b, and A has something like root 3 x1, like which is ith row, plus 5 x2 is equal to 3.4. Now, this root 3 or even 3.4, when we use computer to define it, it never defines the value which is exactly same as root 3. We discussed it earlier, like root 3 is a irrational number, so it will have infinite decimals going on to define exact value of root 3. However, when you use a computer, it truncates it after certain values. So, what we write as what computer writes as root 3 and what root 3 is, there is small difference between them. Therefore, if I look into the ith equation, when I write it in a computer program, it is not the exact ith equation. There are some small values taken out of some of the coefficient, or some small values added to some of these coefficients, and we call that this is a perturbed equation. The equation is not the exact equation, there is small perturbation on the equation. Now, keeping this in mind that we are never solving the exact equation which we are writing in pen paper. When we are translating it into a computer program, whatever be the precision of the computer, whatever be the accuracy of the computer program, there will be small perturbations because due to round off error, because root 3 will be replaced by some value which is very close to root 3 but not exactly root 3. 1 by 3 will be replaced by some value which is 0.3333333 and it will be cut somewhere. It is not exactly 1 by 3, it is very close to 1 by 3. Same for all real numbers probably except integers. So, the equations are little perturbed, we are not solving the exact equation. Now, if we think of a matrix with very high condition number which is A is equal to 1.001111 and we try to find out the eigenvalues. The eigenvalues are 2.005 and 0.00005. Therefore, it has a large condition number to the order of 2 into 10 to the power 4, 4 into 10 to the power 4 something. Now, if I look into the equation, say Ax is equal to, or Axy is equal to say 2 2 and we solve it, we will get x is equal to 0, y is equal to 2. And if we have another equation Axy is equal to 2.00012, we solve it, we will get x is equal to 1, y is equal to 1. So, for very small difference in one particular place, the equations are giving entirely different results. And why they are giving entirely different result? Because it is a large condition number matrix. So, if we have some small perturbation, instead of 2.0001, if it is 2.00005, we can see a very different solution. So, with very small changes in the matrix or in the B vector, the equations change to a great extent, and they are called an unstable equation system, or the matrix solver operating on that will be unstable, though the solution in pen paper can be obtained very easily, but the solutions are heavily perturbed by the round of error, and this happens for matrices with large condition numbers, and we call them to be ill conditioned matrix. In that sense, matrices with low condition numbers are better to deal with. So, condition number, or finding out singular value and finding out the ratios of singular value and finding condition number, is an important task when looking for matrix solvers, and later we will see we will discuss about few more matrix solvers in subsequent classes, and we will see that a lot of matrix solvers actually do not work for matrices where the condition number is bad, or works very inefficiently for very high in condition matrices or high condition number matrices. So, these are few important concepts: positive definiteness, condition number, singular values, which will appear in the next classes with at certain locations, and we have to utilize these concepts to understand the applications in where the matrix solvers are involved. Okay. Thank you.